Today we want to learn residue theorem. Residue theorem is a theorem in complex analysis that assists us to evaluate integrals in complex analysis. So we want to give some definitions. The first one is singular points. Any point at which f of z fails to be analytic, that is where the derivative does not exist, is called a singular point. This one is also can be called singularity. For example, if you look at this function, we discover that this particular function is not defined when z minus 1 is equal to 0. That is, the denominator is equal to 0, which implies that z is equal to 1. So at z is equal to 1, this particular function is not defined. So we now say that this particular function is not analytic at z is equal to 1. So the point z is equal to 1 is called a singular point. There are different types of singular points. One of them is called a pole. So let's now give a definition of a pole. What do we mean by a pole? We say that a pole, or if f of z has a singular pole at z is equal to z naught, and for some natural number n, limit of z goes to z naught into z minus z naught raised to power n f of z, if that limit is equal to a, and a is not equal to 0, then the singular point z naught is called a pole of order n. For example, let's look at this function. We discover that if z plus 4 is equal to 0, this function, the whole of this function, is not defined. Therefore, z is equal to minus 4 is called a singular point. It's called a singular point. It's called a singular point. So, and because if you evaluate this limit, z plus 4 raised to power 2 of f of z, we have limit of 2z as z goes to minus 4. Now, you believe with me that we can have this z plus 4 raised to power 2, then your f of z is 2z divided by z plus 4 raised to power 2. So this and this will cancel. Then we are left with 2z. So that's why we got our 2z here. And if you now substitute minus 4 into this one, it will be 2 multiplied by minus 4, and that will be 8, minus 8. And minus 8 is not equal to 0. Therefore, z is equal to minus 4 is a pole. And because the power to which that particular factor is raised is 2, then we say that it is a pole of order 2, where you can also say double pole. So what does the residue theorem now say? Residue theorem now says that let f of z be single valued and analytic inside and on a simple closed curve C, except at the singularities A, B, C inside C. If you look at this diagram, so we have A, B, C, and the contour is tagged as C, which have residues A1, B1, C1, and so on. Then the residue theorem says that integral of f of z dz in that closed curve C is equal to 2 pi I into A1 plus B1 plus C1 plus and so on. So that is the integral of f of z around C is 2 pi I times the sum of the residues of f of z at the singularities enclosed by C. Now let's go to another definition. How do we now calculate the residue of a pole? Now let z equals to minus a be a pole of order k. Then the residue an is equal to limit of z goes to a of 1 divided by k minus 1 factorial dk minus 1 over dz minus 1 open bracket z minus a raised to power k f of z. And if z is equal to 1, and if k is equal to 1, simple pole, then an is equal to limit of z minus af of z from with z goes to a. So let's look at some examples here. How do we now calculate the residue? Example. Calculate the residues of f of z equals z divided by z minus 1 into z plus 1 raised to power 2. Solution. Looking at this function, we discover that z minus 1, z plus 1 raised to power 2 is equal to 0 gives z is equal to 1 and z is equal to minus 1 twice. So we now have z is equal to 1 as a pole of order 1 and z is equal to minus 1 as a pole of order 2 twice, or order 2. So at z is equal to 1, at z is equal to 1, the residue a1, something like that, will be equal to limit as z goes to 1 of z minus 1 f of z, and this will be equal to that will be equal to limit as z goes to 1 into z minus 1. F of z will be z over z minus 1, then into z plus 1. Z plus 1 raised to power 2. So with this one, and this one cancels. So we now have limit as z goes to 1 of z by z plus 1, everything raised to power 2. So the next thing for us is to differentiate. To evaluate the integral. So we now have 1 over 1 plus 1 raised to power 2, which is 1 over 2 squared, and the result is 1 over 4. So that is the residue of z is equal to 1. Now, we calculate the residue at z is equal to minus 1. In this case, our k is equal to 2. So the residue will now be a2 to be limit as z goes to minus 1 into 1 over 2 minus 1 factorial, the 2 minus 1 over the z, 2 minus 1 is going by the definition of the residue. So z plus 1 raised to power 2. Then we introduce our z. Z divided by z minus 1 into z plus 1 squared. And if you simplify this, you have limit as z goes to minus 1. And this will be 1 factorial. This is 1 over 1 factorial. So d dz into this one and this will cancel out. So we have z divided by z minus 1. So it is this one that we now differentiate. And the result will now be our limit as z goes to minus 1, then into z minus 1 using quotient rule. 1 minus z multiplied by 1 all divided by z minus 1 everything squared. So that is a quotient rule. And this will be equal to limit as z goes to minus 1 into minus 1. You know, by the time you simplify, so when we open this bracket, this will be z minus 1 minus z. So that will now be minus 1 divided by z minus 1 everything squared. And this will be equal to minus 1 over 4. So that is the residue at z is equal to minus 1. So that is the example that we are going to solve today. Now let me give you exercise. Calculate the residue of the following functions. Following functions. 1. F of z equals z squared plus 1 divided by z plus 1 squared into z squared minus 1. So calculate that. 2. F of z equals 5z divided by z plus 2 raised to power 3. Thank you.